let us write this equation in the infinitesimal form. Our delta x will be equal to omega mu x nu with omega mu nu equals to minus omega mu. So this equation defines the Killing vector corresponding to Lorentz transformations. And so the Killing vector will have three indices, right? So the parameter of transformation, so there will be an index that corresponds to the, this is the proper vector index. And then the parameter of the transformation is an antisymmetric tensor because, well, of this equation. So the Killing vector will look like that. And so this will be equal to delta mu lambda x mu minus delta mu x lambda, such that delta x mu is 1/2 omega nu lambda theta mu lambda. Okay. So next we need to figure out what is the generator of this transformation. So for that we need to transform phi. So delta phi will be equal to phi of x minus omega acting on x minus phi. So this will phi of x. So this is minus omega mu by Taylor expanding x nu d mu phi, and that we can write as 1/2 omega minus 1/2 omega mu. So just raising the indices and using antisymmetry of omega, to write it this way. So then the coefficient here determines the generator of these transformations. And you see that the generator coincides with the angular momentum operator, x d nu minus x nu d nu. So the angular momentum operator is simply a generator of rotations, right? So, but in the theory that has Lorentz invariance, we have additional components here, so it promote this non-relativistic angular momentum to this operator that contains the full set of Lorentz indices. So this is simply the relativistic counterpart of the angular momentum operator in quantum mechanics. So to understand what is the angular momentum of the Dirac field, we need to repeat this calculation using the rules with which Lorentz transformations act on spinors. So let's consider Lorentz transformations of the Dirac equation, of the Dirac field. So for the Dirac field, the transformations will contain an additional element, namely psi will transform with an L. Okay? Because psi now is not a scalar, it has an index. So what will happen is that the coordinate frame rotates, and so we should recalculate the argument of psi to make sure that we evaluate it at the right point. But the rotation itself will act on indices of the psi. So at each point, the spinor will do some rotation depending on what we did for the x. So if we then expand it to linear order in omega, what we will get is there will be the part coming from the expansion of the argument, and that will be the same as in the case of the scalar field. And then there will be an additional term coming from L. So the linear part, the part in L that was linear in omega was proportional to sigma. And so the sigma will make its appearance in this equation. So the generator, the Lorentz generator acting on the Dirac field will have this additional term. So the physical interpretation of this formula is that this part of the Lorentz generator is the orbital angular momentum. And this is spin. Well, as usual, we just in quantum mechanics we call everything. So the spin is the part of the angular momentum that's not orbital. Okay. So we just call the left over here the spin operator, and well, let's look what this spin operator looks like. In particular, to get some intuition of what is the spin of the Dirac field, we may want to go a few steps back and recover the sort of the special part of this operator. In particular, if we restrict our indices to be the spatial indices, we get the usual angular momentum, from which we can get the vectorial form of the angular momentum, which we can identify, well, about which we have some intuition from non-relativistic quantum mechanics. So then we need to contract with ijk and multiply by minus I. Yes?
I have a few questions. One is, now we're seeing a number of L's. L nu, you said, is a generator, a distinct object from the L in the line above that's transforming this thing.
So So the way it is defined is that delta psi is equal to 1/2 omega mu L mu psi. So where delta psi is defined as psi prime, well, as psi nu minus psi alt, okay?
Right, and then, so I'm seeing on the left-hand side of the board an L and an L mu nu.
Yes.
And I was wondering, are they distinct objects? As in one is not simply the same thing as the other, just we wrote the indices explicitly. Are they distinct objects?
No, they're not. It's they're obviously not. Just the formula is the same, right? So, so this is a more general object. Contains also L0I.
Sir,
Yes.
I think she's asking whether or not the L for the spinor transformation is the same as the L of angular momentum.
Isn't on that?
That is
side
on the
of
right
Ah,
hand side of the
oh,
board, where the
okay.
two L's on the left column are the same.
Oh no, they're different because so this this is defined for the scalar
no,
field.
that's
So these
not
are
what I
field
meant.
dependent, right? So L will be different for different fields. Okay, so we know that. So let's call this L Klein-Gordon. And this is L Dirac.
And so right above where you wrote Dirac, on the line immediately above, this psi of x goes to L psi. That line there. So the second line. Right. Yeah. So that contains an L.
That contains an L.
Yes.
Ah, okay.
That's
I'm sorry.
compared
Yes.
to
Yes, that's a different L. Just right. So
Okay.
yeah, I will use the same letter for them anyway, but it's a different object.
So similarly, how in the L that we're saying is the Lorentz generator for the Dirac field, we have that sigma, and above we were treating a sigma that's a generator. So this sigma that we said is the spin operators in this particular context, and above we treated a sigma that was just a general generator. Is there any relationship between those two sigmas?
Well, this is just the same sigma, right? Because the psi is transformed with L, and L is defined by the sigma. So infinitesimal linear part of L is just the sigma.
Okay, so this is
And so therefore it makes its appearance here. So, but this is a general. So this is a general sort of story that the generator of the Lorentz transformations will appear in the will appear in this generalized angular momentum operator.
So this again is this sigma that we're dealing with now is the 1/4 commutator of.
Yes, this is one quarter of the commutator of the Dirac matrices.
Okay. And when you have so all the way on the right, we have the line Lij, and then below that Ji. The last line that you wrote. Where are we getting that Ji from?
So this formula is written by analogy. So we're going backwards in this line of argument. So we know what is the counterpart of this formula. So in principle, we can go back, take its spatial part, which is this guy, and then we can reconstruct Li, which is a vector. That's not necessary to do, but it's it just maybe give us more intuition about what this sigma mu is. So then we should take one. Yeah, so this should be contracted with epsilon jk, sigma jk. So this is what we would normally call Li, the quantum mechanical orbital and angular momentum operator. So what stands here is the spin in the sort of direct sense, which is a vector. So let's calculate what is. So now this sigma jk is a 4x4 matrix. So let's calculate what are the entries of this matrix. So for that we need to commute two Dirac matrices. And here I will write them in an explicit matrix form. So the spatial components of the Dirac matrices, if you remember, they were written in terms of Pauli matrices. K0. And so this boils down to commuting Pauli matrices, and with the help of known formulas, this would be written as epsilon jki times sigma I. So this is obviously a diagonal matrix, right? We multiply two skew diagonal matrices, and then we get diagonal matrix. So from this calculation, we conclude what the spin is. So what we find is that the spin is equal to 1/2 times sigma I. So in a sense, this is the usual Pauli spin given by, so the spin operator is given by sigma matrix, Pauli matrix divided by 1/2. But there are two copies of it in a sense. So the Dirac spinor contains two copies of the Pauli spinor, and the spin act in the same way on them. So eigenvalues of this matrix will be, well, 1/2 and minus 1/2, but there are, each eigenvalue is double. So the conclusion we should draw from this calculation is that the Dirac field describes two spin 1/2 particles. So what's the meaning of the second? I mean, why do we get twice as many degrees of freedom? Yes?
Does it make a difference for the spinor to have an upper and lower?
Yes, it does. So we'll talk about that later.
So here, you say generator is so I was thinking that since the Lorentz transformation can be both rotation and translation boost, so what about it? Does the boost also indicate the generator is a true?
Well, this extra piece that we get by promoting the indices to the Lorentz indices is precisely the generator of the boosts. So the usual angular momentum from this calculation should be clear that it generates the spatial rotations, and that the boosts are generated by the generator where one of these indices is 0. So what is this extra degree of freedom? Why we got 2 particles? Well, as we will see later, this particle is actually is an antiparticle in the sense that it has opposite charge, the particle that is described by the Dirac equation. So I mean, this doubling of the degrees of freedom was very confusing. When Dirac first derived his equation, he was extremely confused because, I mean, he wanted to build a theory of an electron, and then the equation required an existence of another particle that was completely the same as electron but had an opposite charge. So the equation, in this sense, predicts the existence of positrons. And positron was not discovered at that time. So later we'll see how all this works. Well, the interpretation that these particles have spin 1/2 just follows from this formula. So we see that the spin part of the angular momentum is given in terms of Pauli matrices. So these particles have spin 1/2. Now, from the mathematical perspective, this doubling of components just means that the spinor representation is reducible. So actually, if you write down sigma mu, so all of the components of sigma mu, then one can see that all components of sigma mu are block diagonal. So there is something standing on the diagonal, but in this 2 by 2 form, the off-diagonal components are 0. So this means that Lorentz transformations act separately on. So if you decompose our spinor into upper doublet and the lower doublet, then Lorentz transformations act separately on psi L and psi right. So in other words, if we do Lorentz transformation, so what will happen is that the components of the spinor will also undergo some linear change, but the components of chi L and chi R never mix. So chi L will transform through itself, and chi right will transform through itself. So they transform independently, and they have a name to them. So this is called the left-handed spinor. 2 dimensions, 2 component spin. and this is called right-handed. And so in principle, they're independently, they're transforming under Lorentz transformations independently. So now the question arises, why do we need the two? Can we live with just one, two component object? Yes?
Sorry, to be clear, is the letter there chi?
Yes.
All right.
So the question is, can we formulate the theory just in terms of these two component objects? And the answer is actually yes. But there are reasons why four-component spinors are sort of more ubiquitous. So we'll return to that when we'll discuss fermions without mass. So for fermions without mass, we'll see that, okay, in the equation, so it turns out that in the Dirac equation, actually, the left and the right components of the spinor, they are mixed. But if we set mass to 0, then the equations completely decompose. Okay, so this is so far how the spinors transformed under Lorentz transformations. Now, another question that we will need to answer is how to take a Hermitian conjugation of the spinor. And it turns out that the Hermitian conjugation is not really useful. Is not so useful for spinors. So there are another type of conjugation that's called Dirac conjugation. So this has to do with this lowering and raising indices issue that, as a result, forming a conjugate spinor is not that trivial in Dirac theory. Namely, suppose that we want to build so psi can be interpreted as some wave function of something. So suppose that we want to consider a number density made of this wave function. So that we take psi dagger and multiply it by psi. And here I mean that it is implied that we contract the spinor indices. The question is if this is a Lorentz scalar. Well, we can of course immediately check this because we know how psi transforms. So this will transform to L dagger L. So there will be L dagger L appearing in the middle. And if our transformations were unitary, this would just cancel. But it turns out that the spinor transformations of, so the transformations acting on the spinors are not unitary. So spinors do not form a unitary representation of the Lorentz group. Meaning that this is not equal to 1. In fact, vector representation of the Lorentz group is also not unitary. And that's the reason why we need to lower the index to contract that vectors, right? We have to contract vectors with covectors. So something similar has to be done here. We should contract psi with something else. So there should be a linear transformation that sort of lowers the index. That's similar to lowering the indices on the vectors. So how to define this operation depends on what happens to the generators when we conjugate, when we take their Hermitian conjugate. Well, since generators are built from the Dirac matrices, at least the infinitesimal generators are built from the Dirac matrices, first we need to understand how to take a Hermitian conjugate of the Dirac matrix. So if you look at the explicit expressions, then it turns out that the spatial and time-like components of the Dirac matrices have different hermiticity. So that's actually very easy to understand. Because gamma 0 squares to +1 and gamma I squared to -1. And of course, Hermitian matrix naturally would square to 1, but if a matrix squares to -1, it better be anti-Hermitian, right? So these two equations can be written in a unified way if we so the Hermitian conjugation is the same as multiplication by gamma 0 from the left and from the right. So if index mu is 0, then what we get here is gamma 0 squared. So only gamma 0 remains. We get this equation. Now, if this is a spatial index, then gamma 0 can be anti-commuted to the right, and then squares to 1. And so this equation is also satisfied. So now L for infinitesimal transformation is 1 plus 1/2 omega mu sigma mu plus etc. And so we need to understand how sigma mu transforms under Hermitian conjugation. So since this is an anti-commutator of two matrices, then what will happen is that it will change a sign, and then there will be a multiplication by gamma 0 from the left and from the right. So the conjugate of L then will be equal to gamma 0, 1 minus 1/2 omega mu sigma mu plus etc. gamma 0. And so you see that the linear part changes sign. And in fact, what happens is that the whole thing combines into the inverse matrix. Yes?
Sorry, would you mind repeating where we got the formula for the Hermitian conjugation of sigma?
So let's do it step by step. So sigma mu is 1/2 1/4 commutator gamma nu, Hermitian conjugate. So Hermitian conjugation, it interchanges the order in which matrices are operated. So this will be 1/4 of gamma nu, dagger gamma nu, dagger. So then we use the general formula for conjugation of the Dirac matrices that can be replaced by multiplication with gamma 0. Now gamma 0s, they appear only outside the commutator and cancel everywhere in between. And so this is the same sigma mu, but with indices interchanged. So using antisymmetry of the commutator, we find that this is minus sigma mu gamma 0. Okay, so the important equation is this one. And so what this equation tells us is that we can define the conjugation of the spinor, and this is called Dirac conjugation, by multiplying the Hermitian conjugate spinor with the gamma 0. So why is this a good definition? Well, just because the conjugate spinor transforms with L dagger, then this L dagger is gamma 0, L minus 1, gamma 0, and then another gamma 0. Gamma 0 squares to 1, and so this is psi bar L minus 1. So multiplying by gamma 0 sort of combines L, so it makes L minus 1 from L dagger. And so now, for instance, if you take a product of psi bar and psi, then this will transform to psi bar L minus 1 L psi, so which is equal to psi bar psi. So we conclude that psi bar psi is a scalar. Is invariant under Lorentz transformations. Now one can also check that psi bar gamma mu psi is a vector using the defining equation for L's. So what will happen is that when we transform psi's, we'll get L minus 1 here and L there. And then we know that conjugating L with conjugating gamma with the L's is the same as rotating the index, the vector index mu. So this will transform as a vector. And if you insert several Dirac matrices, so for instance, if you insert sigma mu, this would be a rank 2 tensor. And so on. So the quantities that have right transformation or simple transformation properties under Lorentz transformations are obtained by using the Dirac conjugate spinor instead of the Hermitian conjugate spinor. Okay, I'll stop here. Thank you. And if you, yes.